I'm normally a semiconductor specialist. I speak about chips, I speak about architectures. And what was asked of me in this presentation was to describe some of the emerging technologies and silicon for high-performance computing. We're in this weird situation now where we've had a good steady 10, 15, 20 years of x86 and then GPUs and now ARM, and everybody's comfortable with that. But we're essentially coming to an era now where there are more chips that can do more things than ever before, and some of it's driven by AI, and I'll get into that. So in this talk, I want to speak about this new HPC era. I'm going to go over the types of legacy hardware that we should all be familiar with, and I've got a few samples to pass around for you to look at. I do need them back. And this is one of the benefits of actually being on site. You actually get to see some of the silicon. I'm going to go through some of the new paradigms in computing. Some of them are new, some of them are old, but they're getting a new burst of funding because of all the new technologies we've developed. So analog, neuro, quantum, optical, there's a few there that I'll probably be missing as well. And then I'm going to speak about why AI chips matter in this push to low precision and how low precision is actually being implemented in HPC as well. And then I want to go through an extended discussion about AI hardware because it is a very vibrant, fast-paced market, not only for the silicon, but also the software. We have new AI models coming out every week, and everybody trusts them or trains them or tests them. And then we have GPT and ChatGPT and OpenAI and all these Lambda funky things coming around. But I'm going to focus mostly on the AI hardware and how it pertains to HPC so you can see some of the architectures that are being involved and are being put in play here. I'm going to go through some case studies. There's a few chip companies that I work with quite closely that I can give some insights in, some roadmaps into the hardware, and also a little bit about the software stacks. One API, ROCm, some vendor-specific ones. I did actually reach out to AMD to get an up-to-date version of ROCm because apparently that was quite well requested. Unfortunately, we never made that happen, but I'll tell you what I know. A little bit about me, because I wouldn't be an influencer if I didn't do some self-promotion. My name's Ian Cutress. Even though I say influencer, I'm actually an industry independent analyst. I work with companies on their technical messaging and try and guide them to describe what they're doing in a way that appeals to a technical audience. Very much these companies in their marketing teams, they're marketers, they're not technical, and there's some disconnect between engineering and marketing. So I help a lot of companies through that. And then, as I said, my YouTube channel called TechTechPotato. On the right here is a video I did with IBM. They took me through their quantum roadmap strategy. That video is approaching 500,000 views. It just so happens I posted it the same week the Nobel Prize went to quantum computing, so that kind of helped. On the left, I'll talk about it a bit later, but this is a new project that I'm doing with Sally Ward-Foxton from EE Times called the AI Hardware Show. 12 episodes. Each episode we cover 6 AI chips that are exciting to us. But I really like it. I actually published the after show second episode podcast this morning, so I'll have to see how that's doing later. And all my background's essentially in computational chemistry as well. I was programming GPUs back when it was CUDA 2.0. I haven't really touched them since, but there we go. And yeah, so let's start off with this title of Silicon or Survive. We're in this new HPC era, but let's go through the legacy types of hardware. So CPUs, everybody's familiar with x86. I hope everybody's familiar with Intel, AMD, VIA, not really. Centaur's just been bought by Intel. And then we also have ARM, upcoming lots of ARM HPC chips as well. Ampere, Fugaku, Nuvia is the exciting one from Qualcomm. I'll get into a bit of that. And then I don't have a slide on power, but power still exists, right? Intel CPUs. So the latest generation Intel CPU here is Sapphire Rapids. We've gone from Lakes and we're now on Rapids. You're probably very familiar with Skylake. That was the very popular 2016 architecture. It powers a lot of supercomputers today. Sapphire Rapids is new and exciting because it's using chiplets. You see on the top left, we've got 4 massive chips. That's 1,600 square millimeters of silicon. They could only do that using extended advanced packaging because your limit per chip is actually about 800 square millimeters in modern manufacturing. So with that, they can put 56 cores on a chip with a bunch of additional accelerators. On the top right and bottom left, you see these little gray bars that are beside it. That's HBM. So they're now putting HBM on their CPUs up to 64 gigs. These are special models specifically for HPC. You can run these CPUs without any DRAM. So we're going to see some installs that are highly dense without any need for DRAM. If you actually look at the cost of a modern server these days, if you want 2 terabytes of DRAM, your main cost is actually the memory. CPU is kind of inconsequential whether you get 16 or 64 cores or what have you. So this is a way to kind of introduce additional density into a modern server platform. And on the bottom right here is the Aurora configuration, which is 2 Sapphire Rapids CPUs connected to 6 of their new, they're calling it GPU Max, everybody calls it Ponte Vecchio, but we'll get into that. And I've got some numbers as well afterwards. And this is AMD's Genoa. So AMD are now back in the x86 game. If you've been asleep under a rock, they now have anywhere between 20 to 30% of the server market, depending which analyst you believe. And their approach for the last 4 generations now has been this chiplet design. They're doing a more basic version of advanced packaging than Intel, but it means that they can have up to 96 cores on a chip now. These are high-performance x86 running at 4 gigahertz cores for about 350 watts. We're seeing a lot of interest now in AMD because they've got 4 generations of their new high-performance architecture under their belt, pushing the frequency. And obviously, if you're familiar with the top supercomputers of the day, a few of them are now using Genoa. And this chip is absolutely massive. This is where I should, straying away from the microphone, I've got here 1 Genoa and 1 Sapphire Rapids CPUs. For those of you on the stream who can't see this, what these companies now like to do with people in the press like me is hand out basically dead CPUs encased in lucite as a paperweight, and basically just to show it off, because now, because media is moving from written to a more visual medium, this is why I've got into YouTube and video, they now essentially want to show these off to everybody just so they can show something on stream that isn't essentially behind a glass case at an event once in a while. So now those sit up in my office alongside a few others. I highly encourage companies to do this if anybody is watching. Very much like silicon in lucite, it's very fun. So x86, let's move on to ARM. The big ARM chip in HPC that everybody knows about now is Fugaku, running so many cores, high performance, #1 supercomputer, or it used to be. And this is a fully custom design, ARM version 8.2, but the key thing here is the scalable vector extensions. If you're familiar with Intel and AVX 512, this is essentially that on steroids with HBM, and Fugaku has been involved in Gordon Bell prizes and research into the COVID-19 pandemic. But this is an ARM-based CPU using standard ARM instructions. And if we actually look at the top 500 list, I decided to go back 15 years to see where the top computers are and what architecture they're using on the CPUs. This is all 500 systems. If we look at 2018, Intel's at about 3/4, AMD's 12%, Power is 12%, so IBM's still there, and there's a spark left, but that's the final spark. Going forward to November 2022, now I know there's going to be a new list coming up at International Supercomputing here in a couple of weeks, but Intel's roughly stayed the same. AMD has taken essentially all of Power. There are still a couple of Power systems left, powered with NVIDIA GPUs as well. But yeah, it just showing where we are in the top 500, Intel is still predominant in the systems that are currently installed. If we look at the new systems, it's more pivoting towards AMD, but Intel still has the majority of it. This is because Intel has roots deep in partners like HPE, Lenovo, Inspur, all the good stuff that supplies some of these supercomputer systems. So that's CPUs. Let's go on to GPUs. NVIDIA, AMD are obviously the big ones, and I've got Intel here as a question mark because they're coming thick and they're coming fast. NVIDIA, everybody should be familiar with NVIDIA using the software CUDA and PTX instructions. Latest generation chip is the H100, H for Hopper. 80 billion transistors, 4 nanometer process. This is Jensen. This is actually, I think, an AI version of Jensen. They did one of their presentations where it was mostly Jensen trained by AI, so he didn't actually need to do much for that presentation. And if you watch an NVIDIA presentation these days, they will have things fly, lots of special AI-driven special effects. So they'll have human segmentation. They'll change the background. They'll increase the number of spatulas behind him because he does some presentations from his kitchen. I think with actually this system, he took it out of the oven because he said it was ready. We're currently seeing these on eBay selling for about 40,000, the Hopper GPUs. But it's a massive chip, lots of HBM memory, and people are clamoring hand over fist for them because they're really good for AI. AMD's latest chip is the MI250X. It's a big chip because it's a bit of a cop-out. It's actually 2 chips packaged together with lots of HBM. It does mean that this is normally the FP64 leader in compute. I think it's something like 93.7 teraflops theoretical peak. Actual peak, you're probably getting around 50 to 60 on a good matrix multiply. But the point here is that they're doing this for density, not necessarily for programmability or ease of use. This chip still looks like 2 GPUs in the system. There's no real benefit to any additional bandwidth between the chips. And the standard Cray-Shas system up the top there is 2 CPUs and essentially 4 MI250Xs. On the bottom left is the MI300 generation, which we'll get onto later, which should be coming out later this year. Now, Intel's a bit different. Intel is always a bit different. Having not really been in the GPU space for quite a long time, headed up by Raj Kaduri, who has now since left, their HPC push on the GPU space is with their architecture, with their chip called Ponte Vecchio, or GPU Max. This is an impressive chip because imagine what we saw with packaging with Genoa and Sapphire Rapids, and then put it to the power. This is 47 tiles. So where we saw Genoa, the CPU, with 13, this is 47. Some of it is stacked vertically, some of it is horizontal. And if you have a 1% package loss yield per chiplet, this means that this would yield about 63% because there's 47 of them. They don't do it that way. But this chip is designed to have essentially equal FP32, FP64 performance, around the 52 teraflops at about 600 watts. And it also does integer 8 performance for low precision, which we'll get to in a bit. This is what's going in Aurora supercomputer, about 20,000 of them. And we'll see this in a second. But again, systems in the top 500 to do with accelerators today, 163 of them are NVIDIA, over 90%. AMD's got 5%, and there are a couple of others like the PZ stuff and what have you. If we look at the R-peak compute in exaflops, just the sum of the systems, NVIDIA and AMD are about equal because the AMD systems are massive installs. But if we add Aurora to that mix, we actually get thirds. So if you're planning your compute strategy based on the total compute sum in the market, you'd say 30, 30, 30, when in fact it's 90% NVIDIA still. So the other benefit of it NVIDIA has is that they have 10 times more engineers than AMD. So any feature you want from an AMD system, NVIDIA is going to have 10 times more people working on it. But it's fun. It means that there's competition. It means that there's going to be a lot of hardware toing and froing. Everybody's going to be trying to get a good deal on their hardware. Everybody's going to be pushing for power efficiency. Whether it works or not is up to you guys, I guess. And then a little thing about FPGAs, because there are some FPGAs in the mix here. 2 big companies historically Altera and Xilinx, now owned by Intel and AMD, respectively. They just needed that additional portion of their portfolio. AMD's portfolio is made up of Vertex FPGAs. These are the big EDA FPGAs, the ones that you do chip simulations on. VU19P, when it was launched 2017, I think, is still practically one of the biggest FPGAs in the market and is very useful for that sort of thing. We now have, at the bottom left, versions with HBM. So they clearly know that they need high-performance memory next to high-performance compute. Field programmable gate arrays, you can essentially program what you like. But down in the bottom right here is their new generation of products called the ACAP, Adaptable Compute Advanced Platform, or something similar. Instead of having a pure programmable logic solution, you have some programmable logic, then you have some DSPs that are hardened, AI accelerators, you have some ARM cores, some real-time ARM cores, and a lot of fixed I/O if you need the memory, if you need PCIe, if you need security, if you need accelerated crypto engines. So it just reduces how much of the field programmable capability you have and provides something that a lot of Xilinx's customers want. These are still very expensive as well. Intel, on the other hand, their product family is called Agilex. And Agilex had a bit of a rough birth. So when Intel purchased Altera, they essentially said, scrap what you're doing, build everything for Intel 10 nanometer. If you know the story about Intel 10 nanometer and how it struggled to get out the door, and it's one of the reasons why Intel is now behind in manufacturing, it meant that essentially the Altera division didn't have any brand new products for several years. They are now slowly coming out on what is called Intel 7, which is the third generation of Intel 10. A lot of people still call it 10++, if you're familiar with the nomenclature. But they now have these FPGAs for low performance, mid performance, high performance, some with HBM, some with advanced networking. And the idea is that with their advanced packaging technology, as you can see here, in most of the pictures, you can attach 400 gig Ethernet or additional accelerator chiplets or PCI chiplets or transceivers, basically big wide SerDes links. And in the top left, you've also got CXL, which is a future technology. I would speak about some of the other FPGA players like Lattice, though they are decidedly more in the mid-range. But what FPGAs actually get most for used a lot for in modern HPC is something called SmartNICs. So I've listed this here under the ASIC section because there's a range, and this is the 2021 Serve the Home, which is another media organization you should absolutely be reading, their Network Interface Card Continuum. So what is a SmartNIC? A SmartNIC is your network card that does smart things to the data as it goes through. So it's not simply a quote-unquote passive device. Maybe you will need to do some advanced routing on the networking card, or you need to do some encryption, decryption. Maybe you need to do some packet analysis of the data coming in and out of your system. If you're talking about a big HPC system, then it's routing is a main thing to make sure you have optimal bandwidth. In the cloud, so AWS, Azure, Google, they'll be doing this for additional security and their quality of service, making sure they meet minimum SLAs for their clients. And is it deployed in use heavily in private clouds and private systems as well. For example, there's a setup using smart networking where instead of transferring data between two systems, it only transfers the difference of data between time steps. And you get additional compression if you only, so say you've got 0.0001, in decimal format, you can, or in a floating point format, you can compress it a lot better than if you're actually sending over 12.386, whatever. So SmartNICs can help with that as well. And actually, I'll get onto the system that uses that. This is another ASIC. If you've heard of DE Shaw Research, they have an ASIC called the Anton, and they announced Anton 3 a couple of years ago now. This DE Shaw Research is headed up by is a hedge fund manager / scientist who made his money on Wall Street and now has a research department that is his plaything to write research papers for molecular dynamics. And as part of that, they built their own silicon just for molecular dynamics. I'm not talking FPGA. They actually taped out with pure ASICs. And molecular dynamics, obviously, you're fighting against all the maths that's involved, plus how many atoms you can put in a simulation. And there's a video of this talk up at the Hot Chips conference. I absolutely loved it because my background's in chemistry. But the whole point is they're trying to do more than what you can do with any other hardware that I've mentioned so far, this talk. And the key graph is this. This is molecular dynamics performance. So if you have your custom silicon, simulation size on the x-axis, and the performance in microseconds per day on a log scale on the y-axis. And we see here that the best GPUs are that gray band, the best conventional supercomputers are the green band, and you can do 100x more with larger simulations using custom hardware. This is the benefit of having a custom ASIC. And this is also one of the reasons why I'm going to be speaking about the AI hardware, because if you can take benefit of it, the speed ups are enormous. And so let me go on to new paradigms, because those are all classical compute situations, essentially, even with a custom ASICs. We've got new/old series computing, or analog computing. So the idea is you have a digital analog converter, pass it through a matrix of resistors with essentially known resistor values, and you get your values out. Lots of benefits: super low power, super low latency, and arguably you can have any value possible. What happens is you actually cut off your values if they're depending on your conversion ratio, and that's where some of the issue happens. You also get elements with nonlinear responses. Can you predict what your multiplication is actually going to be in the analog domain? And then scaling these things out, it has always been tricky. Key players, if you're interested in the companies involved in this: Mythic AI, who were dead, are now back. IBM's also working on some analog stuff now, and Aspinity is a fun little company that tries to do a round with actually doing the digital to analog conversion. So you actually have an analog input from a sensor. That's fun. Neuromorphic computing, and I'll caveat this with a warning, because neuromorphic in the UK especially has been, part of the ecosystem for so many years. If you've heard of Spinnaker, that's what the thing on the right is. That's using spiking neural networks. So it's trying to act like the brain with actually spiking neurons and axons, and you do your calculation, then turning on what happens, you get your output, which is also a spike, and it's also in the time domain. There are companies today who have neuromorphic in the name who aren't doing anything like this. They're just doing pure digital compute, and the reason why they call themselves neuromorphic is because they are brain-inspired. Well, screw you. Key players here, the ones that most people have heard of, is the Intel Loihi chip. This is normally a research-only chip right now. You have to be involved in their Intel Labs program to get a hold of it, but they just launched a second generation. It's built on Intel's most advanced process node technology. I think I've actually got a slide in here about it. And then we also have Spinnaker, which I think is in Manchester. So Intel Loihi 2. So normally in a neuromorphic setting, you would think of it kind of like analog computing with spikes coming through and seeing peaks. Intel's able to do it in a purely digital domain, but still have that spiking behavior. And the key metrics here are on the bottom left. If you guys in the room can't see it, but maximum neurons, we're talking about 1 million neurons per chip, 100 million synapses per chip. And the point is, if you have 100 of these chips, maybe you can simulate a mouse brain, or at least have as many neurons as a mouse brain, in a pure 2D fashion. I spoke to, we'll see him in a second, but Jim Keller, who's a very famous chip designer, he told me that the brain, if you look at the neurons, rather than it being a 2D mesh, is actually about 6 neurons deep, so there's some 3D. So there's still that to do on the neuromorphic design. Way beyond my pay grade, but quantum computing, I'll use this image again because I like the fact that this video did really well. But quantum computing is the technology that everybody says, well, when is it going to be ready? What can it do? It's the 10-year technology that will be ready in 10 years' time. But the simple answer to what it can do, there are three main areas. One, the physical world, so physics, chemistry, biology. Second is math and encryption. So the big example use case, for example, is Shor's algorithm in order to break symmetric and asymmetric key encryption. And then we have machine learning, and obviously you've got to have machine learning on a slide about quantum computing because we are in the machine learning AI era. But there is work going on about this. Again, I partnered with IBM for this video, so I'm very familiar with IBM's function right now. They have over 1,000 research papers currently using quantum computers. There are 20 quantum computers in the cloud that people can sign up to use and pay to use. There are even certain amounts you can use for free. They have an online simulator, so if you want to simulate up to 4 qubits, thankfully all the situations where 4 qubits would be useful have already been known, so it's just a lookup table. But Intel last year said that they were the problem with simulating qubits is if you add another qubit, you square how much compute power you need. So they were able to say that they were able to simulate 44 qubits using most of India's cloud system, some 300,000 systems. But reality is we need about 1 billion qubits, and you're not going to simulate that very easily. There's a high barrier to entry, and it doesn't really do any other mathematics. The point here is that the way you approach problems changes so significantly, it's very hard for classical computing experts to transfer over without a deep course in quantum mechanics. But there are several types of qubits available. Like I say, it's a very active research area, even though nobody's really making any money on it right now. I think the key thing to take away from this slide is what's on the left. You have key metrics in quantum computing that matter when you're doing your compute. You have coherence time, so how long your qubits stay relevant before you essentially have to spin them back up again to make sure that they're coherent. Ion trap is very good. It's over 1 second. Superconducting, so that's when you're cooling it down to 10 millikelvin. They've actually got that up to milliseconds now. This is an IMEX slide from a few years ago. Semiconducting, so this is using standard manufacturing processes that we see silicon on today with spin, and that's 28 milliseconds, and then NV sensors is this one that nobody's really interested much in. But the point is qubits and scalability. The number of qubits that you can do on each process right now reliably, we'll see a slide in a second, but superconducting is now up to about 400, but it's the scalability you need to focus on. If we need 1 billion qubits, you need something that scales. If you don't have something that scales, there's no point researching it. And Google did a great slide here, which I've copied. Thanks, Google. Where the problem that you have with these qubits is error correction. Especially the superconducting ones, the environmental noise matters because that disturbs what your qubit can do. And then you essentially need to collapse the wave function and bring it back up again. In order to make sure that doesn't happen, you need some form of error correction, as with standard memory would do. But you're looking at a ratio of about 100 to 1,000 qubits, physical qubits, for one logical qubit. So when I say you need 1 billion qubits, that gives you 1 million actual compute qubits to work with. And this is why you need scaling. And if we look at the Googles here, so in 2019, they had 54, which could theoretically go beyond classical compute. 2023, you have 100, 2025, you have 1,000, and then the timeline will get longer and longer because we have to discover how these things scale. And this actually doesn't come quite well out on this screen, but this is where we are in IBM's quantum roadmap. Again, because I'm more familiar with them. At the end of last year, they announced Osprey, their 433 qubit chip that goes in one of those massive dilution refrigerators down to 10 millikelvin. And they do something called a heavy hex architecture where the qubits can only be entangled with the ones next to it. And then each one has to be profiled by the residence time. And if you've ever done any testing of memory and how long a memory cell can keep its charge, it's kind of like that. Most can do pretty well, but there are some that are really bad. So when you have an architecture like this, you have to get around the redundancy, and it's quite difficult. But they have a strong roadmap through to 23, 24, 25, 1,000 qubits, all the way up to 4,000. And the key differentiator here is going to be how you take one chip and connect it to another. Right now, all that we've been doing is getting bigger quantum chips. But that scaling ends. So at some point, you have to be able to, for example, connect it to another system. How do we do that and maintain the expansion of qubits that we can use? The other thing that's not mentioned so much here is the software stack. IBM has an open source software stack that's called Qiskit, which is online, free to use. And I didn't put it in here, but they've run over, I think it's over 10 trillion circuits in the cloud in the last 3 years. And more users, lots of free time, or you can pay time. I think it's something about $2.70 per second. But in that second, you can do, say, 10,000 what they call shots of just pushing the data through. It's expensive, but fun, and we're waiting for it to actually cross over where it actually becomes viable. Now I want to move over to optical computing. Optical sounds fun. It's the speed of light, right? If you can compute at the speed of light, then we don't need anything else. Compute happens because we can move light through silicon in something called a waveguide, which is what you have on the left here. This is about 200, I forget the scale, whether it's microns or nanometers. 200 by 100, and the idea is that with the waveguide you can push your light through, and in order for it to compute you need a switch. Transistors are switches, right? And the key switch that most people are using today in optical computing is the Mach-Zehnder interferometer, MZI, sorry, I'm too used to speaking to Americans. And the whole idea is that if you split your light and you apply a voltage bias on one side, you can bring it in and out of phase, and that's your switch. So here we have a differential phase diagram, and if you get the voltage exactly right, you can either have full power or no power, and then that data can continue further down. And you put a lot together, and you get switches, transistors, like a compute platform. And if you actually look at some of these diagrams, so this is a company called Light Matter on the left and Light Intelligence on the right. Light Elegance, I should say. It's a terrible name. And if you actually look at some of the diagrams of how these work, the Light Matter front panel of their server is actually quite fun, because that's kind of what it looks like. The idea is that you have this single beam of light, and it's either switching or not switching. The problem is you're limited to essentially 1-bit compute, almost. And but benefits, no power and speed of light fast. That's really good, or at least speed of light in silicon. The problem right now is manufacturing and its scaling. If you're dealing with this, we're currently dealing with transistors on the nanometer scale, not the 543 nanometers that people talk about, because they're just names, but you have gate widths of 26 to 40 nanometers. If we're dealing with waveguides in the 200 range, then you don't get that level of density. And lots of research is being done on how to make adders, subtractors, multipliers with light. The problem is with those interferometers, if you mistune it so that you only get 98% of your light through, cascade it down 1,000, 10,000 switches, you've now got no light because they're all out of tune. So that's why manufacturing has a serious issue here. And this is an example of Light Matter's chip, Mars. It's built in 12 nanometer low power. I think it's a Global Foundries actually. So 1 gigahertz, but it does a 64 by 64 bit matrix at 200 picoseconds on 150 square millimeters. Power sounds great. Latency sounds great. Density doesn't sound great. And then you've also got this laser coming in off chip because it's not actually generated on chip and you have to power the laser. But we don't often count that. The push in the research is that eventually we'll be able to, we can generate light on the chip and then essentially dissipate it on the chip as well. But scaling that down and actually doing it in a power efficient way is difficult. I realize I'm 40 minutes in and I'm only a third of the way through my slides. So push for low precision. I've gone through a lot of chips here that deal with FP64, FP32, and I know that's what the HPC community is comfortable with. But I want to talk about quantization. Now, what does FP64, what does FP32, what does FP16 actually mean? Well, it determines how well your range of your numbers you can represent are and how accurate they can be. So FP32 and FP16, we have a sign bit, we have an exponent and a mantissa, and if I bring up this slide, it might make more sense. So this equation is almost correct if 2's complement and other stuff makes it slightly different, but whatever. But it's all defined by IEEE 754 standard. We know what it's going to do if it errors out, if they're normal, subnormal. But the important thing here is it's actually, I've taken this from a Qualcomm slide. if you have a 32-bit floating point number, 3452.3194, maybe you can represent that as an 8-bit integer. So you've reduced the number of bits you need to a quarter, and it's still roughly the same, assuming your calculation is amenable to losing a little bit of precision, which is essentially what AI is. And one of the problems with quantization is how you actually represent the numbers. So any number format, you can't represent all numbers because you're limited by the fact you don't have a million bits to represent it. So you have to either clip it or round it. And when you typecast from an FP32 to an integer 8, you're going to have some loss in that level of accuracy, and it depends on, especially with floating point, what format you're going to and from. Now, these are all the floating point formats I found, and I can tell you what they're all used for. So FP32 at the top, standard, everybody should know that. TF32 is NVIDIA's TensorFlow 32-bit representation. What it's done is it's cut down the exponent, but you've still got, you cut down the mantissa, but you still got the exponent. FP16 is one that's being researched in AI right now. And you have BF16, which is Google's BrainFloat 16. And what they've done is they've taken bits and put them on the exponent because you get a different level of range of accuracy, and that's better for machine learning. FP12 is a weird one that I found. FP8 is what's being researched a lot right now in AI. And you'll see these representations of E3, M4. So exponent, 3 bits, mantissa, 4 bits. And with FP8, if you change how many bits you use for each, you can either focus on precision, range, or something else. Tesla is using this quite extensively in their chip Dojo. FP24 and FP21 are internal GPU formats, GPUs that deal with visualization. Vector compute will sometimes use these internal versions. MS FP12 is Microsoft's FP12 format. What you have is essentially 4 bits, so an FP4, but then a fixed 8-bit mantissa width for all of them. So you're essentially defining the range in which those FP4 numbers can run, and then you have FP4, which IBM is researching. FP2 technically exists, and technically so does FP1, which I think is just a sign bit. But we have IBM leading research and quantization. They're looking at it for artificial intelligence, the idea being that, well, if you have 8-bit, 4-bit, 2-bit, rather than having the speed of 64-bit, let's amplify it out. But in terms of HPC, all HPC runs are FP64, FP32, right? No. So on Isambard at Bristol, FP16 on climate and weather, research was done to see speed up versus FP64 and also maintain accuracy, though that's not on the graph. This was done with the A64FX chip that's in Fugaku. And the reason why I bring it up is because this is now a very innovative space in HPC. Can we apply reduced precision to our HPC workloads? If you look at international supercomputing coming up in a couple of weeks, these are all the talks on reduced precision. And there's a name on the bottom right called Jack Dongara. He's pretty important, and he wants to talk about it, so I think everybody should listen. And the point is, if we've got some fluid dynamics, or some more fluid dynamics, or you're doing some particle, or you're doing heat transfer simulations, maybe out here, you don't need FP64. Maybe you're happy with FP8. So you can speed up that bit of the simulation. Yeah, if you need right close, FP64. But if you have a library that does the right amount of quantization at any given point, you can speed up your simulation and be happy with the accuracy of the result. This slide, apologies, it's come out pretty bad. But this is taken at ISSEC, another IEEE conference. And it's showing exponent and mantissa for all different types in the middle. But on the right, it's the amount of flops taken per joule. So how many flops can you get per unit of energy? And if you can run your simulation in FP8, then you get 32x, or BF16, 12.5x versus standard FP32 and FP64. So this is why there's a push for quantization. You can go through the spec sheets for NVIDIA GPUs. They show FP64, FP32. You've got BF16, FP16, Int8, Int4. 2,500 tops of Int4 performance. That's quite a lot. But yeah, so that was quantization. I hope none of that was too new for you, but the reason why it's driven is the AI hardware market. And we have established players in AI hardware. You should all know these companies. I hope you do. But some of the chips I've gone through, some of them I haven't. So we've got NVIDIA, Hopper, Ampere, Volta, Pascal maybe even used these days. For training, AWS has its own training chip, and there's rumors that they're working on something new recently. Google has this tensor processing units, V4, V3, and Intel has at least 5 that they've binned, and these are the 5 that they actually use. Inference is a different workload. So training versus inference, I haven't really got a slide here, but training is the compute-heavy one. Inference is the one that actually works on your phone, just to put into context. And we've got different hardware here. NVIDIA does some very specific inference hardware, the A10, the T4s, and Intel has Greco, but all the CPUs do it, all the GPUs do it as well. I kind of wanted to limit this to ones that you can buy on the shelf. Obviously, you can't buy the Google stuff or the Amazon stuff, but the rest you can. A lot of the chips I'm going to talk about now will be limited to very specific installations, but will be quite important. And the point is that there are over 50 hardware startups doing this. I think at least 70. If you go down into the nitty-gritty of edge computing, there may be over 200. But the market for investment in this is over 10 billion. And this is not the latest numbers, but from September last year, how much money is in all these companies that do AI hardware. At the top is Horizon Robotics, which is a Chinese company doing smart city stuff at 2.2 billion. Sambanova, over $1 billion. Cerebras, GraphCore, UK-based, OnFlame, Ampere Computing, Grok, Sci5, Nuvia, TensTorrent, and a few others that are playing around with VC funding to try and get. We'll come back to this slide a few times, hopefully, but going through some of the chips here. So Google, this isn't the latest, this is the V2, but the V4 is kind of similar. The way their architecture works is that it's a massive matrix multiply systolic array. So it's like a heartbeat. On every clock, the result from the output of one multiply accumulate goes into the next, goes into the next, goes into the next. So you're not doing an operation going back to the scheduler to sort something out and then coming back and then coming through. No, you're not going to a cache. You're just simply passing the data onto the next element unit. The version 1 had one big 256 by 256 matrix multiply array. Version 2 had 128 by 128. I think V4 has 4 of them. The point is, because AI is dealing with lots of matrix multiply and matrix operations, you don't want your matrix too big because that wastes power, but too small and it becomes less efficient. And Google were one of the first to be working with reduced precision as well. That's why they invented the BF16 format. And a system kind of looks like that, which is goes into their custom racks. Or you can rent a pod. This is 64 of their TPUs. I think their V4 pod you can have 4,096 now, and it is petahops, exaops of AI-based compute. Next, I want to talk about Sambanova, which is a company you may not have heard of. Most of their customers are in the defense sector, but they make a chip as big as your hand, which is quite substantial. That's the SN30. It's the SN10 that they've actually been studying recently. 7 nanometer, and it's their architecture is what's called a CGRA. It's coarse-grained reconfigurable array. Think FPGA, but a bit more restrictive, a bit more ASIC-like. So each one of these elements can either be a floating point unit or memory or a little bit of both, but there's some defined network architecture. And the idea is that when you have an operation, rather than the systolic array just essentially pulsating through like a wave, you can have a calculation that just goes between these 4 elements, and it can be programmed at compile time to just go around. So it looks like lower utilization, but you get compute density as a result. And in the map of where what it looks like compared to CPUs, FPGAs, and ASICs, the general consensus is that CGRA is applicable to a lot of aspects. And like I say, their big customers are in defense. So defense kind of likes them. Defense also liked FPGAs as well. But they're starting to now get clients in academic situations. So that's another example of what their specific CGRA architecture looks like in their first generation. They should be coming up with a second generation kind of soon. And the idea is, yeah, you can also bring your algorithm through different elements. So we've got the first orange area is compute, and then the blue area is memory, then through more compute, then memory, or it's doing normals and sums and min-maxes and what have you. And yeah, Sambanova just got a system added to Fugaku to help boost help boost performance of the supercomputer. The idea is that if you have a large search space with your compute, maybe you can condense the search space down by using AI. We're going to see another chip slightly differently that is attached to a supercomputer in a different way, and that chip is Cerebrus. Now, what's the biggest chip you can think of? Is it that big? That's one chip. Size of a dinner plate. I say it's as big as your head. It looks like there's like, I don't know, 64, 70 little chips on that. What they're doing is they're working with TSMC and they have custom interconnect between the chips that they actually put down, which they've got patents for. And it means that they can make one big 24 kilowatt chip, which means you don't have to go off chip if you need more memory or if you need more compute. So they're seeing good examples. People use NVIDIA GPUs and you realize, oh, I don't have enough compute, I need to scale out, or I don't have enough memory to scale out. What if you could just put two GPUs on the same piece of silicon? That's what that is. Largest chip ever built. It has a place in TSMC's History Museum now. Built on 7 nanometer, 46,000 square millimeters silicon. The Sapphire Rapids was 1,600 and the AMD one was about 1,200. 2.6 trillion transistors. If you hear Intel talk about having a 1 trillion transistor chip by the end of the decade, it's already here. 800,000 cores, 40 gigs of on-chip memory. Yeah, TSMC 7 nanometer. And there's two at the Pittsburgh Supercomputing Center. It cost them $5 million, so $2.5 million each. Most expensive chip you'll ever buy, but also the single biggest chip you'll ever buy. They won't give me one in Lucite, by the way, I've asked. They gave me one that was printed on like a metal poster that you can stick on your wall. But the point of adding it to at PSC is, again, for the AI that we discussed with the Sambanova system and Fugaku. But they also do stencil compute with it. So this is meant to be sort of a heat transfer between two planes. So you're literally doing standard HPC code on one of these massive chips. Because it's a massive 2D array of compute elements, if you can funnel your data into the next element, well, I think I've got a slide here showing that half the chip is actually cache. So if you're thinking about, well, how do I include time steps or halos in my stencil compute, you can just all fit it in memory. Yeah. So every core, every one of the 850,000 has 48 kilobytes of high density SRAM. Imagine having each kernel in your CUDA code with 48 kilobytes. Runs at 1.1 gigahertz. Each core runs at 30 milliwatts. But again, it's 24 kilowatts. So try putting that into your Slurm manager and see how many people like it. TENS torrent. This is Jim Keller, who I mentioned earlier. He's worked at Intel, AMD, Tesla, Apple. Basically built all the big chips that now sell in the billions. He now runs a company called TENS Torrent, which is an AI startup with about 700 million in funding. This is me interviewing him at Santa Clara office with their 2nd gen and 3rd gen part. I'm happy to say that they're now a client of mine, which is kind of fun. The whole point of their chip is compute is fine, but the importance is going to be networking. So each one of these chips at the bottom here, I think it's this generation, has 1,600 gig Ethernet ports on it. And the idea is that you connect that to either 16 chips or 64 chips in either a big array, depending on your topology, such that you have a system that can look like a massive 2D array of tensor cores to do your AI compute. Obviously, when you have 16 connections per chip, that's a lot of cables. I asked him how much the cables cost relative to the system, and he said about half. But the point here is that if you're not doing wafer scale and you've got to think about big compute, you need lots of networking. I mean, how many compute problems are bandwidth limited, either memory or networking? This was essentially designed to try and help with that. But they've got a couple of generations going further in the works, one of which has a high-performance RISC-V core, which I've got a video on if you're interested. And yeah, there's a lot of money coming in. There's some money coming out. Okay, I took GraphCore out. So GraphCore, AI company in the UK, one of the first to the market with AI chips. Here it's what, 700 million in funding. The latest report said that they have a revenue of 5 million and a burn rate of 200, which it should be the other way around. But one of the reasons with that is they were the first on the scene. They didn't preempt transformer networks, which are big in AI right now. They're more focused on the previous versions of network CNNs. So they need to pivot quite quickly into a next generation chip. But they do some funky things with packaging, and some of us are hopeful. So in the last few minutes, let's go through some roadmaps on hardware. So Intel just did their DCAI, Data Center Artificial Intelligence roadmap, showing that today we have 4th gen, which is a Sapphire Rapids I showed around. We've got a 5th gen coming. This, I think, is going to be called 6th gen, but it's the second line here that's going to be interesting. So most of the time, we're used to just having performance cores, just one core across the whole chip, and it doesn't matter where the workload rests on the chip, you know the performance of that core. Intel, in the latest consumer products, followed what mobile's been doing, and they now have efficiency cores. These are lower performance, but also lower energy, higher efficiency cores. They're not going to mix and match on server, thankfully, but they now are going to produce chips which are just the efficiency cores. So these cores physically are smaller, but the idea is that you get more compute per joule, and that's apparently what cloud providers have been asking for. Don't know how much relevance they're going to have in HPC yet, but there's been such a demand for it that Intel and AMD, as we'll see in a second, are going down this route of having, instead of 56 cores of your high-performance cores that we're all used to, you have 144 of your efficiency cores, which obviously has considerations with memory and networking and such. As I said, Intel has a lot of hardware going on right now. That was CPUs. GPUs, the Ponte Vecchio, the 47 tile one, they actually just canned the next generation of that called Rialto Bridge, and now we're going on to Falcon Shores, which is meant to be this CPU, GPU, memory mix. There's a lot going on. They have hardware called Gaudi, which is being used by Mobileye right now. That's very much AI-based, FP8 and FP16 based, and then they have the FPGAs as well. And they're also accelerating manufacturing. If you listen to the news, the 5 process nodes in 4 years. Intel's going from its slowest process node ramp to its fastest process node ramp ever. And the person behind it is a very strong-willed Irish woman called Anne Kelleher, who I believe, because she is the person who speaks with authority. I have an interview with her as well that you should definitely watch. NVIDIA also have a roadmap, though they're not too keen on saying much about it. We've just had the Hopper H100 launch. They also are starting a new CPU program in the middle here called Grace. That's going to be ARM Neoverse base. And then they also acquired Mellanox recently. So now they also have Mellanox networking that's going to be built into the GPUs, or at least on the same card as the GPUs. And this slide is showing Grace Hopper. So Grace, their new ARM-based CPU, paired with Hopper, their current, their latest launch GPU, but you have a 900 gigabyte per second interface between the two. So you don't buy a CPU and a GPU now, you just buy a single one package and that's it in your system. Or if you just want the CPU, you can buy 2 lots of the CPUs. Each one of these has 72 ARM cores, so you have a total of 144 cores. And they've done some estimated spec rate numbers as well. The idea is that these will both be available by actually fairly soon. And if you want a diagram, it kind of looks like that. They're doing some interesting things with how each accesses memory and unified memory tables as well, which is going to be nice and complex if you have people sharing a system. AMD, so I passed around the Genoa chip we saw with all those chiplets. They're going to do a cloud native version with 128 cores. These are the smaller, more efficient cores. As far as they haven't announced exactly what that's going to be called, but we think it's just going to be a reduced cache version because some workloads don't need that much cache. Genoa X is their vcache. So imagine having 8 cores with an additional 64 megs of L3 cache on. So for your memory limited workloads, that turns out quite well. They did Milan X last generation, and Genoa X is a new generation. And they're doing a telco version one, a telco focused version one called Sienna. This generation upgrades to DDR5, so you got that update as well. No HBM version yet. Their counter to HBM is essentially the vcache, which is a halfway house, but not really, but it's a lot cheaper. And then on the GPU side, we've got, I went through MI200. MI300 is their new APU, so that's CPU plus GPU plus HBM all in the same package. Kind of like Grace Hopper, but AMD's variant. And they're building the software stack to do that. That should be coming out later this year. And then we have ARM. I haven't mentioned ARM much. ARM don't speak to me much these days. But they have the V platform is their V series. That's for high performance and HPC. N series is their networking. So Amazon's using a variety of these, and E for efficiency. And then the other ARM users include Nuvia, Qualcomm. They're going to be doing a chip, but they're custom designing their own core because of ARM's licensing. You either use one of theirs or you just take the instruction set. TensTorrent also has a roadmap. I showed you G.Skill and Wormhole in that picture with me with Jim Keller. They're working on Black Hole and Grendel. And their whole thing here is that let's make a 128 core RISC-V chip for servers. Let's also make it a chiplet which you can attach to memory or additional compute like a GPU or AI. But that's more in the 2024 timeframe. And yeah, I'm going to wrap up now. Software, CUDA. This is my weak spot because I don't keep up with the software. But CUDA is extensive. It's been around for goodness knows how long, and this is really why NVIDIA have the hold in the market. Lots of libraries. AMD has ROCm. If you must have heard of ROCm before. It took a long while to get ready. It's still kinda. Yeah, I'll leave it at that. But their key here is that they want to translate CUDA code to AMD using HIP-5 techniques. The one thing I liked is the extensive release notes for each version, but I still get comments every time I mention it that it doesn't really work. So up to you. Intel has this one API concept where they're using a combination of C++ and SYCL called Data Parallel C++. The whole concept of one API is it's a bit in the sky. It's write one set of code and you can compile that to any hardware underneath that you want with no additional optimization. As long as when you call a library, there's a variant of that library for the hardware that you're using. So they're putting lots of people, lots of resources behind that. They're making some of it open source. And yeah, enable code reuse across architectures and vendors, CPU, GPU, basically everything that Intel makes, and Intel's trying to bring everybody else under their umbrella. So that means one API versions of all their software stacks. Write once, compile often. How hardware agnostic can it really be? But it has required a proper ground-up redesign of Intel's software support. And then you have the HPC toolkit, and different licensing versions for all of these makes it all nice and complex. Speak to your supplier. And there are things I didn't cover in this talk because of time and knowledge and talent. Interconnect, InfiniBand versus Ethernet versus GPU to GPU. There's a lot of discussion going on about this. IBM's working on data sharded parallel concepts where you don't have things like an OR juice in AI. Integrated optics and photonics. I spoke a little bit about optical compute. What really excites me is actually optical networking and photonics, getting chip-to-chip communications with light, and Light Matter's a good company doing that. And then we have new paradigms like CXL, where we can attach more memory to a system and do funky things like big 42U servers, which is fun. Storage, I didn't cover Optane. Optane is fun. I still want Intel to send me some, even though it's technically a dead product now. And then HBM versus DDR, and we've also seen a class of computer memory. And then what the hell is China doing? There are comments that they actually had their first exaflop computer. Some people saw results. Jack Dongara may be one of them, but they didn't actually publish the top 500. And the numbers they do have in Gordon Bell papers are reduced precision numbers, which complicates the matter. Again, another plug. This is AI Hardware Show. That's me and Sally Ward-Fox from EE Times. First episode, we covered these products. We're covering 72 products through the whole of the series. The idea is an episode every week, followed by a 15-minute episode every week, followed by a 30-minute after-show sort of free-form talk. Second episode that just went out, that includes GraphCore and Intel GPU Max. And we've got things like Tesla Dojo, Cerebrus, all the other Intel products, all the other AMD products also coming out on that. And yeah, time for Q&A, but because Ken asked for it, so I wouldn't be an influencer if I didn't have merch. So here's a mug with my logo for you. And if I can get to the end, unfortunately I can't sell them here because of tax reasons, but 20% off code for everybody in here if you really want a mug with a potato eating a wafer, but thank you.
Right, thanks a lot, Ian. We do have time for a couple of questions. I'm happy to steal some minutes of my own talk for that. Do we have any questions in the room?
One question with remark. I think you mentioned.
I'll give you this really small mic just for the remote.
Yeah, another question with remark. I think you mentioned 2 CPUs on the Shasta MI250X. That's not right. There's 1 CPU for 4 GPUs.
Right. It's a raw.
There, so there is 2 CPUs
per blade. Yeah. Yeah.
Because there's a very special connection between CPU and 4 GPUs.
It's the Trento, isn't it? CPU. So yeah.
Yeah. It's really just beyond very slightly changed.
So on that, well, one of the things that Intel and AMD do is they sell a lot of custom CPUs, either variants. We use custom CPU in a sense of different core counts, different cache sizes, and those get sold to all the hyperscalers, Amazon, Azure, Google, what have you. And that actually accounts for 60% of AMD's volume and Intel's volume. And I asked the appropriate people, is this trend going to continue? And they said, yes, we expect more of our CPUs to be custom variants. With Trento, it's actually a hardware customization. And I think we're going to see more of that, which just complicates things on the design. But yeah, so the whole point about chiplets is that you can be a lot more custom, and that's the hope. Well, that's the hope from their side. From our side, it just complicates things too much.
So I have a question on the AI chips.
Yep.
You showed that there's a lot of money being invested there. So I was wondering, if you would have to invest your money, which chip would it be on and why?
So the problem there is that all the companies that I showed are VC funded. They're not publicly traded. So you have to be part of a VC fund. It's tough. The conversation I always have with Sally is that with training versus inference, training is where the big money is usually. And it's very hard to compete with NVIDIA when you have NVIDIA has 90% of the market. So you're fighting over scraps. And it's the companies that have the value add over the others. What are they doing differently to NVIDIA to help them carve out their niche? Cerebrus is doing the whole wafer scale thing, which is doing really well. TensTorrent has that scaling solution, which sounds very promising. And I highlighted the ones that I think would have this unique. So Sam and Nova as well with their CGRA architecture. I think that architecture to the people in the community, it gets a bad rap because the utilization looks low because you're cycling around data and compute in the chip rather than taking it off and doing like a systolic array. So yeah, in terms of startups, those are the ones that I gravitate towards. Just wanting information. There's also companies like Grok who have a very specialized chip for batch one inference. They've got a deterministic chip basically, and that's really impressive. But the question is always customers, and the key thing to look out for with customers for these companies, are they giving their chips away to academics? If they are, then it's because they don't have corporate customers, they don't have B2B customers, and that's, I think, kind of the rabbit hole that GraphCore is going down. I speak to Cerebrus and TensorTorrent, and they say, yeah, no, we've got installations at universities, no problem, because that helps us get the chip out and people actually using the chip and the software stack. And that's fine because they have a bevy of B2B customers to talk about, whereas there are a lot of companies that don't, and they'll say, oh, our customers want to keep quiet. Really? Just not one? Anyway, yeah. So be careful. I think somebody behind you.
Yeah, so I have a specific question about Sapphire Rapids.
Go on.
I was able to play around them.
I'm sorry.
I just didn't really understand the value proposition of the Sapphire Rapids, specifically for AI. It's like, why would you use this instead of PVC or an NVIDIA GPU?
So the point is, one, it's a host, so you don't need anything else. Two, new instruction sets in Sapphire Rapids. You've got the integer 8 operations, DP4A, VNNI. The whole point is you go down the reduced precision route, which yes, other chips do, but again, it's the single chip solution. And I think with the Falcon Shores and the MI300 with a CPU plus GPU plus memory on top, the whole thing is, can you do everything in the one chip? Yeah. Because you need CPUs to be the backend. One thing that I didn't say in the talk about AI is a lot of AI inference is still done on CPUs, even though there are lots of GPUs out there used for training. If you look at the scale of all the AI workloads from inference to training, just in terms of complexity, GPUs, yeah, you could use for all. CPUs you can use for all. But if you actually look at what's used today in the data center, in the cloud, CPUs are actually used for most of the inference. And it's because you can do things like integer 8 operations and they're accelerated. And to a certain extent, they're also systolic in like tensor core style fashion, especially with the DP4A and VNNI. So if you look through the Intel marketing materials, and again, I apologize in advance, if you look at most of the metrics they advertise, it's okay, there's some MLPerf, there's ResNet 50, but it's mostly inference. So think about it in terms of the inference, think about it in terms of the end customer wanting to essentially have a platform that does it and doesn't want the hassle of additional overhead of supporting GPUs. Or Intel does a lot of work in optimizing code as well with its key partners. And if your code is so optimized for one player, it doesn't give you an opportunity to move off to somebody else either. That's like a 10-year commitment deal sort of thing. Intel's in a rough position with Sapphire Rapids just in general. It's fewer cores than AMD. It's very focused in some of its performance peaks, whereas AMD is a bit more general. But inference, I think, is something that they've got a hold on because they also have a very extensive software stack and optimization in there as well. And they will shout at you for 10 hours about it if you want.
Okay, thanks.
We have whoever's asking the questions to the front, ladies.
Yeah. It's going to be better if you move up front because the signal is too weak. You have a question? Because read in line.
You gave a great overview of the hardware, but what does the software look like for all of these new chips? And
yeah, this is the eternal question. Will anything ever unseat CUDA? And the answer is probably no. We have companies on that list like GraphCore, first chip in 2016. If you believe them at 2016, it sounded like their software was ready. Apparently now they're only just getting to version 1.0. So where exactly is it on the scale? A lot of problem with these companies is that, especially the venture capital ones, is that they'll have an idea and they'll start working on it, software, hardware. Maybe they'll have 2/3 or 3/4 software engineers versus hardware engineers, like TensorTorrent does. But then they'll pick up a customer, a very important customer that's giving them their first revenue or batches of revenue. And then they'll dedicate time to helping their specific customer with their specific issue rather than creating a more general platform for everybody to use. I think the advantage that a lot of these companies have is that PyTorch, TensorFlow, Onyx, standard AI frameworks exist. So if you go towards those targets, then all you're dealing with is the underlying compiler and if that works. And obviously additional tweaking and beyond that. And we've got companies now talking about, is there a PTX variant in some of these AI chips, the sort of lower level language, rather than just dealing with a high level CUDA. So that is still going on. There are a few other companies that aren't doing so well are the ones that are compiler driven. They're trying to maximize efficiency through their compiler rather than just simply the architecture. And historically, companies that go compiler first don't tend to do well. So, yeah, NVIDIA, because I started my route into CUDA was that I took the first ever CUDA course in the UK, run by a finance professor who had some money from NVIDIA. And he did a free course, and I went on the same course the next year just to shore up my knowledge. And that was, 2009? So we've got 14, 15 years of dedicated, university-driven training in CUDA. The only other company that can even come close to that is probably Intel, but everybody's still focused on x86. So unless you can get an x86 to Ponte Vecchio or GPU compiler, it's going to be very difficult.
I just have two questions. The first one, you confused me a little bit with the integers. You said 3452 is an 8-bit integer. I thought that's not possible. It's 255 is the maximum.
I was just going off the diagram.
Our colleague Alan O'Kaiser is not here. He explained a bit of this mini floats, and so you have more integers close to 10, pretty much all the numbers up to 10, and then it spreads out 12, 14.
Do you remember where I said the Microsoft FP12 variant, where it was just a bunch of FP4s and then a fixed 8-bit mantissa? So what some companies are doing with those formats is you apply an offset, a bias to the range. So, okay, you can only do, say, 0 to 256, but if you apply a bias of 4,000, it's actually 4,000 to 4,256. Again, Tesla's doing that a lot in their. I should have shown a slide because they're doing extensive work on getting the right floating point format. So even if when you do your typecast to your reduced precision, if all the data is outside your reduced precision format, you're just going to either clamp at 0 or clamp at 1, or min-max. But if you apply the bias, then maybe you can capture all the data and then apply that. And then you have to manage dealing with packets of data either in the same format or different formats, and how's that computed? And that gets difficult very quickly.
The other question I have is, you mentioned the E-cores, it could have many on the chip. It reminded me of Knight's Corner and Knight's Landing, because they also had high efficiency cores, but that wasn't exactly a success. Is it different this time because it's more consumer oriented?
Yes, it's different because the cores don't suck. Simply put, so with the Xeon Phi stuff that you're talking about, initially they used the P54C core, Pentium variant, and then they used Silvermont Atom cores, which were terrible. The Atom cores are, have a reputation of being terrible. With the E cores this generation, I think they're 6 generations on from those Silvermont cores. And that has given Intel an opportunity to do a blank page design. If you go into the architecture, into the microarchitecture of the core, it actually looks like one of the modern P cores, but just reduced in certain aspects. So, for example, there may not be a micro-op cache now, but now we've got dual 3-wide decoders, which can act as a 6-wide decoder, versus a 6-wide decoder that already exists in the P-cores. So the different optimization points for efficiency, but the cores look relatively similar now. And AMD's difference is just, we believe, just cache levels for their E-core variants. But yeah, I've got chips, consumer chips now that are just E-cores. And a modern E-core performs the same as a Skylake core in 2016. So it is performant. It's not today performance, it's 6 years ago's performance, but it's better than being 20 years ago performance.
We have another question in the back. Maybe Ian, you can just repeat the question. It's going to be
Sorry, yes.
No, it's just a problem with the other mic.
Yep.
Sure. So got a couple. One of them is is there any work to incorporate posits
You've been reading my Twitter feed. So the question was about posits, the number formats where you just have more than sign, exponent, mantissa, and lots of other stuff as well. A company did reach out to me called Vivid Sparks, who apparently John Gustafson's on the board, the inventor of posits. So stuff exists, is happening. I haven't looked into it much. I think Vivid Sparks, for example, is fully self-funded at this point, or very early seed backer funded, not a proper Series A funding round. And part of that is also the utility, understanding the where they can be performant and in what sort of workloads they can be useful. Obviously, posits, because of their additional bits to talk about different things, can make them more versatile, but then you're just dealing with more bits anyway. So how do you get around that as well? We've had 50 years of dealing with floating point and integer numbers in the formats we have. We have 0 years of posits. So it's very difficult for them to come in. It's the same with different lithography techniques and stuff. So, but yes. Did you say you had a second?
So the conversation whatever happened to OpenCL, is it completely replaced by SQL?
OpenCL exists. So I haven't kept up to date with it as much. Yeah. So the question is, where has OpenCL gone? Yeah, it exists. It hasn't disappeared like OpenAMP did. Whenever there is a question about data parallel C++ or SQL, it's OpenCL is always mentioned in breath, or Vulkan OpenCL also. So it is still mentioned, and if all the diagrams that I showed, the NVIDIA, the AMD, and even the Intel one, they all mention it as well. So they all still have backends that support it. But obviously the libraries try to be agnostic and the compilers just try to deal with it. So.
Okay, I think we're going to wrap up.
Yep. Thank you.
Thanks a lot, Ian.